at every given point along this transit here. The next thing we need to determine is the velocity that the sand grain is going to fall. We do that with Stokes' law, which simplified is 2 times the radius of the particle. Talk about a gas particle, or I'm sorry, a sand particle, a very, very small diameter. So 2 times the radius of that particle times the difference in the density of the sphere to the density of the fluid that it's falling in. So falling from gas, you're going to have a very big difference between the density of the sand grain and the density of the fluid that it's in. So you're going to fall relatively quickly through the gas phase. Once you get to the liquid, it's going to fall at a different velocity, and the density of the fluid versus the sphere allows you to figure out that's the viscosity of the fluid that you're in too. So viscosity plays somewhat of a role, but on a much lesser scale than gravity's constant. I hope. Using that, we're able to calculate the amount of time that it takes to fall to the bottom, crossed with the amount of time, the velocity of each medium that it's moving through. And in particular with this tilt, you had to keep adding to the distance once it hit the liquid phase. Once it hits the liquid phase, now you have, and that's what makes this version more efficient, is that you have the bottom running away from you, allowing you to have more of a safety factor in how you stop sand inside the vessel. That's accounting for the geometry of the desander. So, looking at the spreadsheet, you can't really, but he went into 100 different steps. Like I said, if you use calculus, you can do it on a continuous basis. For our purposes, in using Excel, steps make more sense. If anybody wants to try to figure out the calculus part.
You need to measure the density and viscosity of your sand constantly, or you assume that fine sand and assume a constant density, or you.
Sometimes our clients will tell us, well, we have very salty water.
Right.
So our specific gravity is consistently 1.1. On the grand scale of things, that will change it, but you're talking about 0.1 with a difference between 2.65 grams per cc and 0.1 gram per cc. It only helps us if the fluid is more dense. So we always assume 1 would be a worst case scenario. Also viscosity, you have to worry about emulsions or any type of gel that is unbroken that comes back, anything that makes your fluid more viscous. You're going to get to a point where the sand is just not going to fall out. If it doesn't fall out in that glass on your desk, it's not going to fall out in our desander. We don't have sand there. We rely on the same thing that operates on the surface. So that can change. And that's why people ask, are you working in the tar sands or in heavy oil plays? And the answer is no, because if you're making high viscosity oil, this velocity is so slow that it doesn't sink to the bottom as fast, and it doesn't stop the sand in our vessel before it carries through the outlet. So, it becomes a pretty big engineering problem in how can we predict how our different vessels are going to work. And as engineers, we don't like just throwing out the same piece of equipment and hoping. Every well we go on, we ask for data from offset wells, and we do this calculation and tell the customer that at the 6-foot mark, that's where your sand's going to fall. And because it falls at the 6-foot mark, we have 20 feet to work with, we'll stop 100% of the sand that comes back up to a certain boundary. And being able to claim 100% efficient, especially as a sales guy, is scary, but because the engineering backs it up, I feel comfortable doing that. Which brings me to my last point, which is we did all this fancy math and physics. We're engineers in an office, everything's great. Excel tells us that it's going to work. When we get out to the field, what happens if it doesn't? Does that mean that physics don't apply? And of course, that's not the case. What happens in the real world is that in the field, you have other variables that you're not accounting for in your model. And so over the first several years that we were running this model and experiencing failures in the field, every time sand carries over, we consider that a failure. And so we would go back and try to figure out why. We'd go in and we'd measure where the end of that dune was. Does it match up with what we predicted? And over the course of a few years, we were able to build real-world experiences into the model. So if our model was saying it's going to fall out at 8 feet, and in reality we saw it fall out at 12 under those circumstances, we're going to discount and build an additional safety factor. And so now when we go in and run our model, we know that it's going to work in the field as well as conceptually using physics. Which is always, I think if there's any takeaway, it's you can do all the math and physics in the world, but verify it with what's actually happening and be flexible enough to change the math, change the physics, and build in some safety factors to make sure that you're predicting what's actually going to happen, not what you wish would happen. So with that, I'll entertain any questions. Yeah? How much does it cost? Okay. Well, a couple of things. We are a rental business, so we're just renting on a monthly basis this equipment to our clients. What's really neat about our piece of equipment versus a lot of equipment that's out there is that ours doesn't wear out. Because we reduce the velocity and keep the energy low, we cannot erode the inside of our pipe. We don't erode the inlet, we don't erode the outlet because we take all the sand out first, and we slow it down enough to where we don't damage our own equipment. Otherwise, we have the possibility of damaging our customers. So we can do our economics over 10 or 12 years with this. These don't wear out. We have units in service now that have been in service since pretty much the inception of the company. So that being said, it costs quite a bit to build these because we build to ASME code. They're ANSI pressure vessels, so they're very, very stout. In fact, our 6,000 PSI vessel is manufactured by having a piece of bar stock 20 feet long that we then forge a hole through because you can't have any seams in the main body of the pressure vessel. Pretty neat process done outside of Chicago that we then import to Canada and fabricate there. So the big upfront cost and the long life of the product allows us to offer to the customer about $10,000 a month, or 300 some a day. And that includes the instrumentation, the scales, the troubleshooting, the electronics, and the fact that we beam up that data to a website, or we'll help them tie into their own data acquisition system on rotation. So it's a pretty reasonable price for what we do. But being a company that's founded on intellectual property and a patent, and the fact that we can keep our units in the field without having to retire them allows us to offer a pretty competitive price. In contrast, the vertical unit I drew over there would be a couple $100 a day, or $40,000 to buy. And so a few months of us, and only when you need us, beats having to spend capital dollars on a piece of equipment that, right now companies were doing 150, 200 wells a year. They bought vertical sand traps for every single well, and now they're starting to pull those off, and they're not drilling that same number of wells anymore. So they have a lot of inventory and just purchased equipment around. Whereas if they would have rented ours only on an as-needed basis, it would save that upfront cost and not have to pay to store them. Does that answer your question? Okay. Yeah.
this sand that gets sucked out after it's filled up, does it get recycled anywhere, or does it just get dumped?
No, it pretty much goes to wherever they're disposing of any of the byproducts that come out of the well. And the big reason for that is the fact that you're only going to get maybe 1% of it back. So what do you really gain by drying it out, making sure it doesn't have radioactive material on it, making sure it doesn't have hydrocarbons? So you're going to have to put it in an oven. You have to burn gas to get maybe 15,000 pounds back and put it into a 1.5 million pound frac job. Practically, there's really no need. So it's cheaper to just send it on with whatever water and cuttings and all the other byproducts of drilling, including the well. It goes to a landfill or some other hazardous waste site where they're permitted to dispose of. Safely. Yeah.
So the benefit to having your desanders isn't in that they're making money off the sand, but it's rather that they're protecting their equipment further down the line?
They protect your equipment, so every piece of washed out equipment you saw has to be replaced. So you're saving the cost of having to replace valves. Certainly that's a huge cost if you blow up the production house there. Right? And you got to pay for the fire department and then all the rest of it. So yeah, there's costs not only monetarily, but imagine if you had neighbors, it would cost you in social license to operate in that area. Not to mention the government likes to investigate those sort of things. It costs money with lawyers and all the rest of the lawsuits.
So because of the, it seems kind of dangerous to have things going wrong because of the sand. Is there any kind of regulations coming about that require a desanding process of some kind?
No, I don't think they're going to be handling it on the regulatory side. The integrity of your pipeline, the integrity of your facilities is a challenge for the operators in general. You have the weather, you have elements, you have corrosion. This is another aspect of facility and equipment integrity. And so, it's really a judgment call to the operators. Are we getting enough sand back to be dangerous? Some companies are keeping their production low, so it keeps their velocities low, so they're not bringing that sand back. They're just postponing that sand coming back and leave it in the well, thinking that leaving it in the well is the best option. In the short term, it may be. Long term, it's going to come eventually. Probably when they're not ready for it. So, from a regulatory perspective, sand is probably not on their radar, but certainly if there were incidents that were to happen, they would start asking questions about why. At that point, then they're off. They're going to put one on every well.
Any other questions?
People mandate it.
Yeah. So the lifetime of a well, how long do you
So the recommendation is until the sand gets to a manageable state. So if a client says, I can handle 3 pounds an hour, now, with our measurement system, they will know exactly when they don't need us anymore. Typically, it's 2 or 3 months, but in markets where they're making irrigation sand, it could be the entire life of the well. Good news is because now that you're measuring it, you know for sure. You're not going to have to guess. So that's a big benefit to actually quantifying sand production. And it's also where the customer sets their tolerable levels of sand. What they think they can handle, what they think is just a nuisance and not really a safety or production problem. 2 or 3 months, you're probably down to 5 pounds an hour around here. But then you shut in the well, the pressure comes up, turn it back in line, and all of a sudden here comes the slug of sand. So, yep. And the flow of gas is dependent upon pressure and temperature, as well as the gas rate itself.
Any other questions? Let's thank our speaker.
You guys want business card or brochures? I put them up here if you want to take a look.
Everybody